Get started, so it's a pleasure to welcome Danna Freedman from MIT to give the physics colloquium today. Dana is a chemist, so try not to hold that against her. She did her undergraduate at Harvard, which sparked an interest in one topic that spans the borders of physics and chemistry, which is magnetic materials. And then went all the way across the country to Berkeley and got her PhD with Jeffrey Long, looking at single molecule magnets and various clusters. Then came all the way back across the country to do a postdoc at MIT, just down the road, as it were, looking at quantum spin liquids and frustrated materials. That's sort of more of a physics, I would argue.
True.
Yes.
Inexplicably, I had a chemistry advisor, but
Yes,
he was the
yes.
product of Caltech, so we can blame Caltech chemistry.
Okay, very good, very good. Then after that postdoc, went to Northwestern as a faculty member, and then not too long after that, went back to MIT to take her current post in the Department of Chemistry. So as I said, her work spans the borders of chemistry and physics, looking at using techniques such as high pressure synthesis, and looking at tunable materials that are tuned for qubit applications, which I think is going to be one of the focuses of your talk today. So hopefully
We'll find out.
We'll find out. Okay, so hopefully that will appeal to both the physicists and the chemists in the audience. So please.
Thanks. Hi, so I'm Danna Freedman. It is great to meet all of you. So, when I was invited for a physics colloquium at Caltech, I was actually really excited because I love hearing about problems that I haven't had the opportunity to think about before. And that's been one of the absolute delights of the past couple of years of having the opportunity to give a number of physics seminars around the country is hear these like really funky to me problems. I mean, as a chemist, who would have thought that adding digits to the G tensor would be something people would care about? And yet it is. And then people talk about it and they're interested, and you see why these problems are so cool to so many people. And so it's really great to have the opportunity to chat with all of you. But I've been getting the feeling from my schedule today that maybe the audience I'm talking to is a little different than what I planned for. So maybe could you raise your hand if you're a physicist? Okay, chemists? Okay, I'll do my best. So that's about, for those of you in front, a 50-50 split. So it's not the easiest split. The other thing is, when I was invited, I thought I was giving a condensed matter talk, which is what half of my group does. But again, after today, I think I'm giving a quantum talk. But what I'd actually like to do, I think I can do this at this late stage in my career. I have a couple of options prepared. I can do straight up molecules for quantum talk, or I can do about 30 minutes on molecules for quantum, then about 15 minutes on condensed matter systems. So that we've been studying. So again, I'm going to ask you to vote for option 1 or option 2. There will be other audience participation, but I can also promise you, I know you have a party. In my career, I have never once gone over time on a talk. And I also am the worst GRC moderator, where I just like stand up and say, you're going to sit down right now, and we're done listening to you. So pick the one you want to hear. It will be the right amount of time. So just molecules, and condensed matter. Okay, just molecules. Molecules and condensed matter. All right, you have a winner. Okay, this is what we're going to do. And I'm going to do my best to manage these topics to this strangely diverse audience of chemists and physicists. So let's begin with molecules for quantum. And so broadly speaking, as a chemist, effectively defining a role for molecules in this field, this is a weird position to be in, right? Talking to a bunch of physicists who know quantum mechanics far better than I do. So thinking about this, if we're thinking about a place for molecules in this broad range of quantum information, whatever words we're using, what are we using at Caltech? What's our like favorite phrase? Quantum ecosystem, quantum, I'm not getting an answer on that one, I know. Okay, so if we're thinking about this, the way I think about this as a chemist is that quantum is highly diverse in the areas that it can impact. And I think about it in the most chemistry-like way, which is this area fundamentally is how we can harness the quantum properties of the world around us to impact different areas. And really my central thesis in this field is that the applications within quantum are so diverse that it would be a little silly if the same unit was the best unit for all applications in quantum. You can imagine an ultra cold atom, which to me is unfathomably cold, but to you is every day, could be the best quantum computer candidate, but it maybe is unlikely to be the best sensor for a biological system. I mean, maybe it could work. But my argument is that in a lot of these areas, what we should be doing is we should be designing towards specific applications and systems where we can control where every atom goes, or at least where most of them go, have promise in this space. Before I move on, I'll also note that any figure in my talk which has no chemical information or scientific information was made by a former student of mine who's starting a graphics design company, and I'm happy to give you his information. Okay, so my argument is, and I've been trying to convince a lot of people that I'm right, but that's generally an uphill battle in my life. We need to think about what the application is and how we can create threads and connections between users and people who are designing systems. In perhaps what might connect with both the chemists and the physicists in this audience, what you can argue is you have a lot of people who are doing great design on quantum computing, great design on quantum algorithms, but thinking about what problem a quantum computer could solve is one where maybe we should talk a little bit more to a chemist. For example, I'm sure many of you are familiar with or complicit in this many-year period where quantum computing folks were saying that they were going to solve the mechanism of nitrogenase with a quantum computer. I mean, I don't think anyone talked to Teo and back. He's actually doing this with a molecule. Not using quantum computing, but these actual connections between people who are working in this space, in my opinion, has a lot of value in designing towards specific goals. Definitely not a quantum computer. Okay, so how do we actually do this? So one thing, and I'm not going to show you anything useful in this talk whatsoever, just to be clear. So what I want to do to talk about why molecules are important in this space is to go back to the very beginning. So how many of you know this paper? This is the same as asking how many physicists there are in the audience, right? And Vernon. So I've been showing this molecule for my entire career and making the argument that molecules are really great at precise location. And so with this molecule, the team of physicists and mathematicians that worked on it were able to precisely position all of these nuclei exactly where they wanted. And they have this system which is tunable, reproducible, and scalable. And it's amazing that every single one of these molecules is identical. I mean, the precision on this fluorine-fluorine distance is ridiculous. Now, I will actually say that I've been saying this for years. And when I moved to MIT, I met Ike, and I very, very nervously, because Ike's terrifying, but wonderful, went up to him and was like, so why did you pick that molecule? And he said I was right. So I'm going to go with that forever, even if he changes his mind. I'm not going to get laughs from this audience either, am I? Okay. I will stop trying. My students say I'm not funny and need to stop trying to make jokes.
Well, give us another chance.
One more. Okay. So the attributes of this molecule, and I think we all know that this type of molecular quantum computing is effectively dead. And there are a lot of reasons that we know that this type of quantum computing is dead. We can talk about frequency crowding and other more physicsy applications. But on the chemistry side, one reason that this is dead is if you were to just magically add a fluorine, you can't do that, to here, it wouldn't just shift, it wouldn't just add another peak, it would shift the whole spectrum. And so this is a real problem, and this is something which is an inherent challenge in this type of NMR-based quantum computing. But these same attributes of reproducibility, precision, controllability can be used for a different application in this space, which is quantum sensing. And so thinking about all of this work and how really beautiful it is, we can think not just about using this for quantum sensing, but we can think about positioning not just nuclei, but also electron spins in different places. And so here, I have this electrons and nuclei. And so what I want to tell you about briefly is some of the work that's been done in chemistry thus far to get to this place, and then I'll talk you through an example of what we do. Now, before I show you this slide, which I wouldn't have shown if I thought there were so many chemists in the audience, I'm just going to offer a quick caveat, which is I showed this slide recently at a conference, and someone came up to me angrily and told me that I hadn't shown their work, and how dare I? So I'm really sorry if I haven't shown your work or your advisor's work. It's designed to make a point, not be inclusive of the whole community. Sorry. Okay, so we can put nuclei and electron spins where we want, and we can control their relative separation. And that's something really challenging to do with other systems. We can also control spin orbit interactions and tune spin delocalization, which is of course a proxy for coupling. We can also tune ligand field, and because there's so many chemists in the room, I hesitate. Do I need to define ligand? Cool, thanks. What?
Also physicists, so they might.
Organic thingy bound to a metal. Thingy is a really useful word. And we'll talk about ligand fields a lot more. These molecules can also be integrated into devices, and this is one of my favorite, this isn't me, results over the past couple of years. This is a single molecule STM measurement, which to the best of my knowledge is the first this type of molecule, single molecule ESR measurement. And as an experimentalist, even though in theory, because there have been measurements on atoms that are single molecule ESR measurements, it should naturally translate to molecules, and there's no theoretical reason why it shouldn't. As an experimentalist, it didn't happen until it happened. So I think that this is a really beautiful proof of concept. Molecules can also tune interspin distance, which is really nice. And you can also imagine using different types of framework approaches from metal organic framework chemistry, coordination polymer chemistry, DNA origami type chemistry, etc., to build out arbitrary networks. And arbitrary networks, I'm going to say again, I am absolutely not talking about quantum computing. I don't think molecules have a competitive advantage for quantum computing, and I'm absolutely not currently arguing for that idea, but there are a lot of reasons that you could need a network of spins. For example, for sensing, you can imagine using that for triangulation. You could imagine precisely positioning something to beat a diffraction limit because you know where the thing is. And so creating networks has a lot of potential for all of those applications. So what do molecules have? Okay. What we need for a molecule is we need some way to initialize it, right? We need some control over coherence properties, however you want to use that, and you need some scalability. In theory, molecules could have all of those, but initialization is really one of the key problems. And so if you're thinking about spin-based qubits and spin-based qubits for sensing, what you probably think about are defects in semiconductors. And there are a lot of defects in semiconductors, or so-called color centers. So here are 3 arbitrarily chosen defects in semiconductors. Okay, for the chemists, I'm just going to tell you a brief embarrassing story. I did not understand why physicists called diamond a semiconductor for a really long period of time, and it deeply upset me until after a seminar 3 years ago, a physicist took me aside and kind of politely explained to me that to physicists, a semiconductor is something you can dope to metallicity. This upsets me as a chemist. An insulator is a thing with a giant 5.5 EV band gap like a diamond, but I accept. So that was mainly for the chemists who may have had a similar experience, not understanding why physicists keep calling diamond a semiconductor. Okay, so we have a bunch of semiconductors with defects in them. And the thing that all these systems have in common, all of the color centers, is you can have optically detected magnetic resonance. Now, from a chemistry perspective, these things look totally different, right? These have absolutely nothing in common. This is ridiculous. I mean, you do have a bunch of insulators or semiconducting lattices, but you have chromium, you have a vacancy in a silicon carbide lattice, you have cerium, that's a lanthanide, you have the anionic nitrogen vacancy pair defect in diamond, which is pretty much a main group element. This collection of things makes no sense from a chemical perspective, and yet they all have this same feature. And so these systems are great, but they also have a couple of challenges if anyone has worked with them. And those challenges could very well be addressed by creating a molecular analog. So diamonds are amazing, but they have some areas for improvement. For example, you have to be about 10 nanometers away from the material you're measuring for spatial control. Distance is important. Now let's just think about this for a second. So why do you have to have your defect buried deep within the diamond? And this is mostly for the chemists, but let's think about this system chemically. We have a nitrogen vacancy pair defect in the middle of diamond. It's anionic, S equals 1. And so effectively what that means is you have your sp3 hybridized vacancy that's also bound to two things. And so that means you have this pentavalent carbon. This is like deeply upsetting. This is what we fail organic chemistry students for doing. We do not attach a carbon to 5 things. Carbon not, like, this is just canonically bad. We have a name for it, it's a Texas carbon. Like this is not a thing we do. And so why does this exist? It exists because the way De Beers makes diamonds is they take a diamond and they shoot ions at it, and we are not under thermodynamic control here, right? This is a kinetic species that we isolate. Put it in the diamond, and then once it's there, if we were to move it over, we create exactly the same thing. So there's no driving force thermodynamically to move it, and then the barrier to breaking it, to moving it, is breaking a carbon-carbon bond. And so this thing persists once we create it, but if there's any chemical way for it to dissipate, it'll dissipate. And so that's also why it has to be buried deep within the surface of the diamond. And that's also why it's really challenging to just look at this thing and say, yeah, I'm going to make that as a molecule. An organic chemist who's better than me could definitely do this. I mean, maybe, but it's really hard. So a different approach, so molecules are great, would be to consider this and to consider that we don't actually want a defect in a diamond. What we want is the electronic structure generated by a color center. So instead of making a smaller version of this, can we build up the electronic structure from the ground up? So how do we do that? I just finished on yesterday teaching my half of undergraduate in organic chemistry, and I will now subject you to it. So we want our ground state, we want our small axial zero field splitting, and we want a highly symmetric state, probably an A state of some kind. And so we want to think about how we would do that. The beauty of inorganic chemistry is we can take a metal and put some ligands around it and tell the d orbitals where to go. It's pretty amazing that we just get to tell the d orbitals where to go. You can imagine that to get an A state, here, nickel 2, let's say, you could throw in 8 electrons, right? And then you would get the right configuration. Here are a collection of other examples of molecules that will give you the same state if you just put the ligands where you want to get those A term states. So I think there are enough chemists. What's the first one? All right, next one. Well, it's distorted, so, and the last one? Yes. I think I heard it, so I'm gonna just animate it, trigonal bipyramidal. Right, we know that we put the ligands where we want them and the d orbitals go in place. And so there are a million different ways that we can create states that work for this. And this is very much the point of this slide and the following ones. There isn't one answer. There are a lot of answers, just like there are many color centers. There are many ways that we can do this with molecules and ways that we can think about tuning these systems. So the next thing that we want to design is the excited state manifold. And so first we were looking at really small energy splittings. Now we're looking at something optical, right? And so what we want is we want our singlet state to be below our triplet state, so we get narrow emission. Okay, so how do we do that? Again, we go back and just by drawing the states on pen and paper, the way we do with the undergrads, we say, okay, our ground state's a triplet. We have an excited state triplet, which is necessarily due to a spin promotion. So that's going to be very sensitive to the ligand field, how many electrons we're donating. And then we have a spin flip transition as our singlet state. And so the singlet state is going to be invariant to the ligand field. Okay, so with this, we know exactly what we want. We just want a strong ligand field. This is so easy, right? Okay, so let's map this onto a resonant excitation scheme, which is what we actually use. We can manipulate using microwaves and then read out the population subsequently. And so let's map this. Here are some options for our triplet A ground state. These are a large collection of molecules and symmetries that would work. We can use trigonal bipyramidal vanadium or chromium. We can use tetrahedral chromium. We can think about nickel. We can think about molybdenum. We also want our singlet state. Our singlet state, if we're using a resonant excitation, our zero field splitting can't be infinitesimally small because we need to be able to selectively address our transition. And so you know all of this. We also need a sufficiently long T1 so we don't randomize the very information that we're trying to read out. Okay, molecules. So here are a series of molecules that meet all of the design parameters that we've described. And so these are organometallic chromium centers. And one thing, to the chemists, this isn't exciting, but to the physicists, you can just like move around this methyl group magically. This is what we do, right? We magically move atoms around. And so as an advisor who doesn't do anything in lab, I'm not supposed to say chemistry is easy because I don't do it anymore and it's still slightly painful for the students, but it is. This is the change between the methyl group here to the methyl group here to the methyl group here is actually easy synthetic chemistry. And so we can just make that trivial change across this series of molecules. And doing that changes our ground state, ESR. I don't even know how to handle this. It's ESR for the physicists and EPR for the chemists, but you're in an equal mix. Parameters. And one thing that you can note is we turn on our rhombic splitting as we move across this series of molecules just by subtly changing the symmetry. The other thing that we do is we subtly change the symmetry of these molecules is we tune the emission frequency, which is something incredibly challenging to do in the solid state. Okay. So we have our beautiful singlet line, which gives us our sharp transition. We can also recapitulate these data through all optical measurements where we resonantly excite and turn on these transitions that we can measure. And so we can also, and by we, I mean in collaboration with the Echelon Lab at the University of Chicago, in particular, an awesome former postdoc there, Sam Bayless, who's now at Glasgow and is awesome. And you should have him out, physicists. Acquire all the same measurements that you can on defects in semiconductors and demonstrate that these molecules have the same features. We can also tune the emission further. And so I told you that this singlet state is invariant to ligand field, but that's like totally a lie, right? I mean, Teo, do you teach undergraduate inorganic chemistry?
Not right now.
But, you know, can you believe I said the singlet state is invariant to ligand field? Heresy. So it does have both some character, as you can see in the slightly more accurate diagram. But the other thing is, when we say the singlet is invariant to ligand field, we're assuming that we have pure D to D transitions. But that's a total lie. That's not how molecular orbital diagrams work. We have ligand and metal character. And so the ligand character helps us with these transitions. And so by expanding this series in what was actually not a synthetically trivial expansion, we can see in collaboration with Tim Birkelbach's lab that when we move through this series, we can control emission, and the quantity of electron density in the pi system helps us determine how we can think about the transition state. And so we can also predictably control the emission frequency. And shown here is controlling it over a relatively narrow range from about 900 to close to 1050, but in other molecules we've looked at, we have a range right now of about 890 to 1550 with emission of these molecules, which is, I think, really fun and a whole area that we can play with. The other thing we can do with these molecules is we can tune their coherence properties. So I think it'll become clear in the second half of the talk, but one of the things that I really love in life, other than magnetism and molecules, and bismuth is my favorite element, is crystallography. I really love crystallography at an irrational level. So if you look at these molecules and you want to think more carefully about why we don't have any rhombic splitting in the first one, that's very easily explained by how they crystallize. And so they crystallize with this S4 axis, and so by symmetry, the rhombic splitting is excluded. So this is the transition that you have. And so I didn't emphasize the T2 times of these molecules because they're like really bad. But if we wanted to extend the T2 times, we can steal a trick from the AMO physicists, and we can look for a transition that's more clock-like. Another brief story. The first time that I tried to talk to physicists about creating clock-like transitions, I didn't say clock-like, I said clock. I was very, very rapidly corrected that a clock transition only occurs in an atom and must be perfect. In a messy molecule, it's clock-like. And I will continue to get that right. But I love this, right? I love that we can take the systems that are really, really precise and map the things that we learn from the really precise systems onto the messy chemical systems that are a little bit closer to the real world. And I think that mapping is really important for whatever it's worth. So how do we change this transition such that we can turn on a clock-like transition? We need some sort of mixing element, and I've already implied we're going to use our rhombic splitting, which indeed we are. So we can change the matrix of these systems to turn on some rhombic splitting. And so to do that, we can take this molecule, which is initially in a matrix with S4 symmetry, change it to a matrix of C1 symmetry, and turn on some rhombic splitting. I would say, to be whatever, this is the equivalent of replacing your diamond with silicon carbide, magically. Julia Galli was able to really beautifully, in my opinion, predict the response to coherence time that we would get from this simple symmetry change. And so what you can see is we've increased our coherence times from, I clicked over the slide, to 10 microseconds, which isn't great, but it is, I think, a very reasonable time. So anyway, you can have a lot of fun with systems like this. So I have 2 more slides on molecules. This next one, I hesitate to show, but I will. Okay, so we have been looking at resonant excitation, but it would be really nice for a lot of reasons to move from resonant to off-resonant excitation, which is one of the key features of the anionic nitrogen vacancy pair defect in diamond. Now, this is, to me, weird. We only observe off-resonant excitation in one of these molecules, and we have no idea why. And we have no idea how to make it better. Anyone want to guess which one it is? I wouldn't have been able to.
Just guess the middle.
It is the middle one.
No, it's not mine.
It wasn't. But so anyway, this is something that we're really confused by, and I would love to chat more. If it's obvious, then can you just tell me after the seminar so I don't look really silly? But we've been struggling with the idea of why only one of these molecules is amenable to off-resonant excitation and how to make the off-resonant excitation stronger. So the other thing I'll say is I told you that molecules could be useful for sensing, and then I also promised you I wouldn't show you anything useful. Let me show you one slide on the type of sensing problem that I think this first generation of molecules could be useful for. So there's a question about some of these 2D magnets, for example, chromium triiodide. So you have these weird systems, and it doesn't make sense, right, that a 2D material should be magnetic or should be a permanent magnet, but chromium triiodide and some of these materials aren't, and this has been an active area of research. So understanding the magnetic field at the surface of these materials is actually surprisingly controversial. There are published measurements of the surface magnetic field of chromium triiodide, that differ by 5 orders of magnitude of the same material, which seems like a lot to me. So this is the type of problem that I think a discrete layer of molecules is useful for. You can imagine taking a layer of molecules, putting it on the chromium triiodide, measuring out magnetic field, HBN molecules, and actually being able to directly read out a magnetic moment at a 1 nanometer range. And so this 1 nanometer to 9 nanometer range of sensing magnetic and electric fields is really difficult to access. And this is one of the potential competitive advantages of molecules, even molecules at low temperature. So, okay, yeah, perfect. Okay, so with that, I am going to end this part of the talk and talk to you about some of the condensed matter stuff we do. This will be slightly more disjointed because I just pulled these slides together this morning. So let's see what we can do. Okay, so let me tell you how we started in this field, just for fun. So when I started my position many years ago, one of the things that I thought it would be fun to do would be to make materials where we take an element that has a lot of spin, an element that has a lot of orbital angular momentum, and put them together and see how close we could get to a lanthanide. This wasn't necessarily the best thought out idea, but the core idea is you take a spin carrier, you take an orbital angular momentum carrier, and you see if you can create a state that sounds like J. And so I've proposed both molecules and materials in this space. The molecules turn out to be really hard to make. The materials hard, but in a different way. But so this was the core question. So if we're trying to think about a spin-bearing element, iron is a pretty good example. What about orbital angular momentum? What has a lot of orbital angular momentum? Heavy things. Does that... Is it fair? Does anyone know what the heaviest element that's stable to radioactive decay other than Nick? It isn't. It's lead. Bismuth decays in slightly longer than the age of the universe, I think. So what you want is something really heavy, right? Bismuth is, we'll call it the heaviest element stable to radioactive decay. So thinking about getting orbital angular momentum from bismuth is something that we were thinking about for a while. Basically, can we take this beautiful source of orbital angular momentum, crash it into things, and make things with new properties? And so the vector, right, we know this, the binary phase diagrams have been worked out for over 100 years. If something was thermodynamically stable, it would be known. So what we need to move into metastable materials. And just as a reminder, right, metastable doesn't mean unstable. Diamond is metastable. Graphite is forever. Graphite. So how did we do this? We tried a lot of different things. The vector that actually worked for us ended up being high pressure. And pressure is a really interesting and I think underused vector. What I'll be talking about here is quasi-hydrostatic pressure, which is pressure in a diamond anvil cell. But you can think about pressure as a far more complex unit. And in recent years, we love stealing things from geophysics. In recent years, there's been a lot more work on shear and isotropic pressure. We're currently doing a bit of work with shear, and I'm not going to have time to talk about this, but my student Kathy is also shooting things. She loves it when I do this to her. So she is shooting bullets at things to use the transient shock wave that's created upon impact to add kinetic resolution to pressure. And so Kathy's using guns to shoot things. She really doesn't appreciate when I do this to her, but what she's doing is really cool. And I hope I'll have the chance to tell you all about that at some point in the future when it's a little less half-baked. Okay, so these are some diamond anvil cells and this worked. So we made some compounds, and I'll show you a few of the compounds we made a little bit later, but more recently, when we've been targeting materials, we've used some trivial computations to help us narrow down what is this expansive phase space. So we've used ab initio random structure search calculations, and here you can just see a quick animation of that, using that, we can apply these calculations to, for example, what looks like an intractable phase diagram. So this is just a standard phase diagram, atomic percent bismuth versus molybdenum, temperature. For those of you that have seen ASM phase diagrams, my students are forbidden from ever showing one of those graphically. They must remake every phase diagram. That is the worst grid database, terrible graphics. So using that structure search approach, we can identify some pressures and find and predict some materials to make. And so using this, we can predict new materials. So here is the first molybdenum bismuth binary. And so the reason, see, he left as soon as I started solid state. Bye, Tim. He had to leave. He's gonna kill me later. Okay, so that's kind of the workflow we've been going through. And using that workflow, we've made a bunch of binary compounds. This is a selection of them that I think are kind of fun. Copper 11 bismuth 7, the first copper bismuth binary is a superconductor. We also made a layered structure of this material that I think could be really cool to study further. Copper lead, nickel lead, and iron bismuth, which is what I'm going to move to talking about. So iron bismuth was, of course, the first thing that we went after. And this is the phase diagram. You can see that iron and bismuth have almost no miscibility. It's a 0.16 weight percent miscibility between the two. And so using pressures that are comparable to the core of Mars, we were able to synthesize the first iron bismuth binary compound. And we were really excited about this for no reason whatsoever. Like, this is just cool. You know, the first iron bismuth binary compound, we get to understand the impact of bismuth on iron, but then we have to come up with a way to do that. And we tried to decompress it and we couldn't. And so now we have this really cool compound. I mean, I'm assuming it's going to be awesome. That's trapped deep within a diamond anvil cell. And so this material is trapped deep within a diamond anvil cell. It's about 100, what you call the surface of the diamond that you use for the pressures, the qubit. It's about 100 micron qubit size. And so this really small sample. There are a lot of reasons it's hard to probe such a thing. You may be familiar with some work others have done trying to study superconductivity in that area. We'll ignore that and the existence of that. You may also be familiar with some work on pressurizing hydrogen and trying to study that. That's for drinks. But anyway, so how do we study this? And so I'm sure the answer is obvious to you based on the first part of my talk and all of your extensive physics knowledge. There is a thing in a diamond, which is called an anionic nitrogen vacancy pair defect, which can be used to sense magnetic fields. And so we've been collaborating with Norm Yao, because this is really hard, too hard for me. Norm's great. To measure the magnetic moment of iron bismuth trapped within a diamond anvil cell. Now, the really cool thing about using a diamond is diamonds are transparent to everything. So what we can do with the diamond anvil cell, 100 microns sounds really small, but we can rasterize like 100 spots and get the diffraction pattern at every one of those spots. And then we can directly correlate our diffraction patterns to our measurements of our magnetic moment. The other thing is, nitrogen vacancy centers naturally have 4 different orientations, right, in the diamond. And so we can use the 4 different orientations relative to an external magnetic field to start to get information about the magnetization of our material. And so what we see is, we see these laser spots, and we see these tiny magnetic dipoles at room temperature that we believe are evidence of permanent magnetism in iron bismuth. And so these are just the first measurements we have. I'm showing you super unpublished data that's very far away from publication, but we're really excited to learn more about this material and to probe its low temperature properties. Actually, today, my students are meeting with Norm's students, but I don't know what they found. So I'm very upset not to know that. We can also use other more conventional techniques like X-ray spectroscopies, and we can use that to probe materials such as manganese bismuth and MnBi2, which is another new material we made, and to demonstrate that's a permanent magnet. You may notice the first of several beavers on this slide, I have a ton of MIT school spirit and I'm very into Tim, our mascot. I hear you all also have a beaver that you're trying to get rid of. I'm pro beaver, but turtles are cute too. Okay, so with that, I am gonna transition to the last like 5 slides of the talk, and I promise you'll be in time for here. So we did all of this work with these materials and we're still studying a lot of them. And I'm also globally interested in collaborations in this space. We've also, and I didn't have time to pull slides on this, looked at some continuous transformations of pressure. For example, driving jarosite, which is an S equals 5/2 Kagome lattice to an S equals 1/2 state to create a spin liquid. Which kind of mimics my postdoc work, which was jointly with Danna, Sarah, and Youngly. Maybe one for each half of the audience. So one problem with materials at high pressure, or materials in general, and materials discovery, is figuring out what they are. So we made a bunch of new materials that we thought would have cool properties, and we can easily get a powder diffraction pattern in a diamond anvil cell, but we couldn't solve these powder patterns, which was really annoying and hurt my ego too, but we couldn't do it. They were totally resistant to Rietveld refinement. So we were playing around with this, and my wonderful student Eric, pictured here, not here, an amazing undergrad in my lab, Zach, decided that they were going to take this on, and this might actually be a good use for artificial intelligence, solving these powder patterns. And so one really good thing about powder diffraction is there are incredibly extensive databases of powder patterns and quality markers exist in them. And so using all of those databases, my students fed an AI program. Well, they wrote all of the code, so I shouldn't say that. But they looked at how we have X-rays, and X-rays reduce information, and decided to turn the powder pattern back into crystallographic information. And so this is an incredibly abbreviated version of what they did, but basically they took the pattern, they converted it, they got an initial random structure, denoised it, and then turned it into something reasonable using a program my student Eric wrote called SnapRock. He's not great at naming these things, but the program's really useful. And then using that, he was able to solve several hundreds of structures that were experimental data in unsolved databases and get good metrics and all of that nonsense. But more important to me, he was able to take the backlog of unsolved structures of new materials from our lab, and this is the processed data, and actually turn them into structures. And because these are our data, we know that they're right because we can probe these materials in other ways and determine that these are indeed the right structures. And so using this, we're much more rapidly refining our structural identification process. And this is, of course, all the code and everything's available online. And Eric claims the GUI will be up soon too. I don't know if I believe him, but everything's of course available online. And so this is the thing that we've been having a lot of fun with lately on the high pressure side, and you should use it. It's great. Okay, so with that, I want to take a minute to acknowledge my students and Tim. And Tim is the MIT mascot, it's MIT backwards, because they do all the work. I also, if you're interested in the intersection of chemistry and quantum information, want to highlight this recent report on advancing chemistry and quantum information science, which I think has a lot of very reasonable ideas in this space. And funding, and you for the invitation and your attention. Thank you.
Thank you very much for the eclectic set of topics. So I'm sure there are questions.
Thanks, Garnet.
Get started. So Danna, it's very curious about you talking about the metastate stability of the phase code, things that you can make.
Yeah.
So how many but the example we picked was something that wasn't metastable, you can take it out of the.
Well, I mean, it depends, right? So there are a few things here. There's metastable under the conditions of formation, and then there's metastable under other conditions, right? So when you're using like an errors approach, you're identifying things that are stable at that point, and then they're metastable as you start to decompose. And so the kinetic stability is due to the decompression, is activated in the decompression, not under the synthetic conditions. So
I'm just curious, like, how many? No, I tend to think if it's not stable, it's just not something that you should make, but how many things were actually stable when you removed them?
yeah, so for example, both of the copper bismuth superconductors that we made, I only showed one. I've like literally held a chunk of it in my hand, and we were able to fully characterize them using standard techniques. The DSC measurements, that was 2014, so grain of salt, but I believe they decomposed at 216 Celsius and 275 Celsius respectively. But that could be a little off. The copper lead system, I think we had it at ambient conditions, but then the student graduated and we haven't revisited. Nickel lead, we had samples. Oh my God. The nickel lead compound, our theoretical collaborators tell us it has an interesting band structure. And we had ARPA's time at Berkeley, March 23rd, 2020. And then a series of things happened and we never managed to follow up on that. And also the student graduated and we'd need to remake it. So I showed diamond anvil cell work, which is very small scale. The other thing we can do is we can use a multi-anvil press, which I didn't show here. There are multi-anvil presses that you can use both with and without an X-ray in them. And so the multi-anvil presses we use to scale up all of the materials that we think will have some quantity of metastability. Brookhaven has a really nice integrated line with an X-ray. So you can see so as you decompress, you can see if you made something in your multi-anvil cell that's worth looking at. And then there are other more extreme approaches. And if you think metastable isn't worth it, then like you have to get rid of all of organic chemistry.
Yeah, methane is. Well, you got, no, I agree, but it's great that you can make many new things just by squeezing it and then.
I agree.
Yeah.
Other questions?
Good talk. I'm just interested in your idea about incorporating spins and angular momentums from different sides. So they say, how would you envision that could happen in, say, your binary, say, iron bismuth too? Like, what kind of interactions would that also be like? That could possibly be.
Are you a chemist or a physicist? Okay, cool. So if you think about this, if you think about bismuth, every individual orbital of bismuth is going to have substantial orbital angular momentum, but you aren't going to have any unpaired spin density on them. And so you have this substantial spin orbit coupling where you're at that weird point with bismuth where your spin orbit coupled states end up, like if you looked at your XPS data, you would have a separation of your p orbitals, right? And so you know that that's going to be relatively large, but you have no unpaired spin density on them. As soon as you have a molecular orbital where you're transferring unpaired spin density into those orbitals that inherently have orbital angular momentum, you're going to have some interaction between your spin and your orbital moment. And so you can think about that either in a molecular picture or in a band picture. But in both of those, you're taking states that have both of those properties and you're bringing them together. And so you should have some contribution from each of them, and it just depends how you build up that picture.
It goes question towards back. Yeah.
So when upon doing XRD measurements with these high pressure instruments, how pure are the phases? Are they like 100% or like what's?
Yeah, great question. So we really do rasterize over many spots, and so you're putting something pretty simple in. So that makes it a lot easier. We've more recently been exploring ternaries where you introduce complication does not scale linearly, but what do you have in the cell? you have the diamond, which ideally is not contacting your sample. But if it does, then you have to think a lot about carbon on the surface of diamond as well. We use MgO that we machine into little discs as both an insulator and a pressure transmitting medium, and actually an internal calibrant, because the equation of state is well developed. And so we can use that to calibrate the pressure. So MgO, 2 more elements. The elements that you put in, if you're using a rhenium gasket, which is usually what we use, the rhenium gasket comes in here. Okay, that's it. So it's pretty easy in general. These powder patterns were infuriating. But in general, for us, it's been relatively easy to determine this because we can move across the material and there are like 3 or 4 different things. Sometimes we get a spot that looks, to the best of our knowledge, diffraction is limited by sample size, etc., to be pure. But if we see something else, it's usually pretty fast to identify what it is, right? We know that bismuth undergoes a series of phase transitions with pressure. We know iron, for example, is probably the best characterized material at high pressure because geophysicists developed these techniques to study the core of the Earth. And so we can just compare to literature data and figure out what our combinations are. We always see MgO, which is good because that's our pressure transmitting medium and it's within the vertical spot size. But yeah, we haven't seen oxygen incorporation with the exception of one thing where we wrote a paper saying we did it on purpose.
So I have I guess a sort of a technical follow-up to that. You answered the first half, which is what sort of, which is the MgO as a pressure transmitting medium. How hydrostatic is the condition inside the cell?
Yeah, I mean, it's a great question. So you can measure with MgO, you can measure with Ruby. We see different variances across the cell, depending on our qubit size, depending on the reaction we're using, depending on our method of heating or not heating. So
I guess the sort of follow-up is how sensitive are your syntheses to pressure gradients?
yeah, so we've had very few syntheses which have a narrow phase stability window. And so the next paper that we publish will be on the cobalt bismuth system. And there we have a couple of really narrow phase stability windows. And we think that there the lack of perfect hydrostatic pressure is a problem. But yeah, so you can measure, you can see GPA variances across the cell, which I think, as you know, is fairly common in these systems, which is why I keep saying quasi-hydrostatic. I don't want to in any way mislead. We think MgO is a really good pressure transmitting medium though, because it's really clean. And we don't love Ruby. Ruby's a problem because of the chemistry a little bit. And so we want to make sure that we don't introduce some of these variables that we don't like into the system. But we have done a lot of reactions with Ruby, especially second reactions where we want to do, so like chemistry doesn't exist if it's not reproducible. Actually, 4 years ago, we made what I'm pretty sure was a material that we were targeting because we think it would be a nictide superconductor, which is a ternary. And we've never been able to reproduce it, so I've never tried to publish it, and I'm so angry about this. It's a really cool material. Definitely existed in that diamond anvil cell. It had bismuth.
So going back to your sensing molecules that you started with, it made this really, to me, an interesting point of sort of going from very simple kinds of crystal structures to molecular structures where you can control atomic arrangements. I'm wondering for sensing whether there be also some advantage to go even bigger to supramolecular structures, like in something like a rotaxane, you can kind of move things around as part of the sensing structure.
Yeah, totally. I think that looking at larger scale things, so I really, really believe what I said at the beginning, which is that you have to design towards the problem. And so where there's something that a responsive element would help you sense something, then that would be interesting. For example, for electric gradient or pH sensing, a responsive element could be really useful to tell you when you've moved from one zone to another. For just like generically, I don't think that a rotaxane would be an ideal target, but you have to think about where your limitation is, what your question is, and then what the thing that you really need is. And so I think that larger systems, one thing that I would think about is beating the diffraction limit. So systems where you can know where they are because of chemistry or because of an external technique, and then it doesn't matter how big your spot size is because you already know where it is. And some larger molecules could be useful for that, especially as you think about different ways to position them.
Right, any other questions?
I guess this is somewhat related. I have a more broad question. So you showed many really interesting molecules and solid systems that you invented. And wondering what's your rationale in like choosing those targets, and especially for the chemical systems that we talked about.
You know, I'm a really simple person. I like questions that I don't know the answer to in general. So if there's something where I think that we can learn something by looking at a system, then I get really excited about it. I was talking in one of my meetings earlier. One of the things that I'm currently inexplicably really into is we're using organic molecules to detect dark matter. I don't know why. I mean, I do know why, but it's just like a fun thing, like working with a bunch of physicists to see if we can do this. And it's a question. I don't have the answer. I can't just play the tape forward and figure out what'll happen next. And so there are a lot of things that I get excited about. And that's one thing that I'm ridiculously lucky to have my job where I get to think about cool things and think about where there are questions, and ideally questions that open up many directions. So that's a very broad answer. I don't know if it helps.
Maybe more specifically, I'm also curious about like what are some like criteria that you think about. So like this is I'm a theorist and I'm interested in thinking like how theory can help design these materials. And so I guess that's why I'm wondering, like from an experimental perspective, like how do you choose or how do you design your targets select your
Yeah, I think to a limit, I like operating in a constrained space. So I think that there's value to not chemistry, but you know, if somebody tells me I'm going to visit Boston and I like this type of food and I like walking and I absolutely don't want to be anywhere near beer. I'm like, oh, perfect, challenge. Like, here's your itinerary. This is exactly what you should do. And that makes me really happy. And so I don't know if the parallel to molecules makes sense, but I like understanding and problem solving in a somewhat constrained space. And so I think that that intersects with theory a little bit. And so if there's like Garnet's working on superconductors, right? I hear. So if you want to think about okay, so like I'll just like replay my conversation with Garnet from earlier today. So Garnet's interested in some superconductors, and I think what's interesting, not to speak for Garnet at all, is systems that aren't literally copper containing systems, but systems that have similar things but are totally structurally different, which is an area that hasn't been explored that I think Garnet is looking at now. But like, what one electron systems exist at the beginning of the periodic table? Like, to me, that's a really exciting problem to think about. How do you think about designing planar systems? When I was a postdoc, I loved the idea of how do you make electrons unhappy by controlling where atoms are. I love making electrons unhappy. These are all really fun problems that exist in a constrained space. And so outlining parameters and maybe a collection of areas to synthetically innovate in is one that I get really excited about. Like if Garnet says vanadium systems are going to make really cool superconductors if you can get them close to sulfur, I'll be like, yes, I'm going to make that, and my students will hate me because they will smell bad. The students, not the students, the materials.
All right, well, I think that's a great note to end on. So thank you again for your great talk.